Welcome to this explainer. If you work in tech, you're probably swimming in data all day long. You totally get metrics, distributions, and algorithms. But when you look at clinical research or medical studies, it often feels like an entirely different, totally opaque language. Well, today, we're going to decode that clinical research using the language you already speak. We're diving deep into the fascinating Evidence-Based Medicine for Techies course, which is a brilliant framework designed specifically for analytical minds who really want to understand how medical evidence is actually weighed and applied in the real world.
We're going to anchor everything we talk about today on this one guiding philosophy. Critical appraisal and evidence-based medicine taught the way a clinician actually thinks, starting with a patient, not a p-value. Because as data-driven as medicine is, clinical data literally only matters when it serves a real, living, breathing human being. This entire course is fundamentally about moving from the patient to asking a well-formed question, judging the evidence, and then bringing it all right back to the patient. All right, here's our roadmap. We've got 1. Evidence-based medicine for techies. 2. The skeptical techies statistics. 3. P-values versus confidence intervals. 4. Significance and p-hacking. 5. Endpoints and reading limitations. And 6. Back to the patient. The goal here is to transform you from a skeptical techie into a highly informed consumer of medical evidence. Let's jump right in. Section 1. Evidence-based medicine for techies. Okay, so the entire approach of this material is built on something called the Vibe Rounds spirit, which revolves around Socratic learning. And in this context, Socratic learning is basically using AI that questions you rather than just handing you the answers. Instead of just spitting out a summary of a medical paper, this method challenges your assumptions. It asks you the right questions before revealing how clinical researchers view those exact same numbers. It's a very active problem-solving approach to learning evidence-based medicine right from first principles.
Section 2. The skeptical techies statistics.
If you don't have a clinical background, you really need a cheat sheet so we can speak the same language. And this perfectly illustrates how clinical concepts map directly to tech principles you already know. So in medicine, they use PICO to formulate clinical questions. For a techie, that's simply your search schema. When you hear randomized controlled trials or RCTs, just think of them as highly rigorous A/B tests. Likelihood ratios in diagnostic testing? Actually, those are just Bayesian updates based on prior probabilities. And grade, used for clinical guidelines, maps beautifully to evaluating your test coverage versus making a final ship decision. By bridging this gap, the whole clinical evidence pyramid suddenly becomes incredibly accessible. Section 3, p-values versus confidence intervals. Now we're hitting the real core of our explainer today. Lesson 8. This is the statistics deep dive specifically engineered for the analytical mind, the skeptical techie. We're starting with the classic clash between two major statistical measures used in practically every medical paper. For a long time, the p-value has been treated as the ultimate decider. But honestly, a p-value is really just a binary statistical flag. It tells you if an effect exists mathematically, but it completely strips away all the context. Confidence intervals, on the other hand, provide a range showing where the true effect actually lies. They give you a much richer, way more nuanced picture of the data's precision and its real-world impact. In the course, you actually learn to work through these by hand, because seeing the spread of that interval tells you infinitely more than a simple Boolean true or false flag ever could. To really hammer home why context and ranges matter way more than static metrics, check out this number, 8%. As teased in the course's Insight section, you might see the exact same diagnostic test give a mere 8% predictive value in one population and a massive 90% predictive value in another. No way, right? But it's true, because prevalence completely changes how useful a test is. If you just look at a static p-value or some generalized metric, you completely miss the reality of the patient sitting right in front of you. Context is absolutely everything. Section 4, significance and p-hacking. So what does the word significant actually claim in clinical research? Well, a significant result just means a statistical threshold was met. It is definitely not a guarantee of real-world clinical importance. A study might find a statistically significant reduction in a symptom, meaning the math checks out, it wasn't just random chance, but if that reduction is so incredibly tiny that the patient can't even feel the difference, it completely lacks clinical importance. As skeptical techies, we have to look past the word significant and ask, okay, significant by what magnitude, and does it actually matter to human health? And because that significance label is so highly prized for getting papers published, we have to be super vigilant against p-hacking.
P-hacking is basically manipulating data, slicing up demographics, or running endless statistical analyses until non-significant results falsely appear significant. It's exactly like running an A/B test on your website, finding no overall lift in sales, but then drilling down until you find that, left-handed users on Tuesdays bought slightly more and declaring the whole test a success. Lesson 8 emphasizes that to spot these statistical illusions, you have to critically read the limitation sections of these studies. That is where the bodies are buried.
Section 5, Endpoints and Reading Limitations.
Let's transition and see how studies actually measure success in the first place. This brings us to surrogate endpoints, and Lesson 8 warns us heavily about these. There are substitute metrics used in trials instead of direct clinical outcomes. For example, a drug might successfully lower blood pressure or cholesterol. That's the surrogate endpoint, and it looks fantastic on a chart. But the direct clinical outcome we actually care about is, does it prevent heart attacks and keep the patient alive? Sometimes an intervention hits the surrogate endpoint beautifully, but totally fails to improve the actual health of the patient. If you're reading a study, you always have to check if they're celebrating a proxy metric or a real-world victory.
To help navigate this massive sea of data, limitations, and endpoints, the course provides an awesome framework for using a large language model as a clinician's research assistant. First, the AI drafts your search strategy and extracts the methodology. Second, you humanly stress test that appraisal. And third, and this is a hard, unbreakable rule, the AI drafts, but you, the human, must manually verify every single number and citation against the original source material. It's a real game changer of a workflow, provided you never blindly trust the output.
Section 6. Back to the patient.
Finally, after mastering RCTs, confidence intervals, and surrogate endpoints, we arrive at the culmination of the course, Lesson 9. Remember that quote from the very beginning? We start with a patient, not a p-value. In this final phase, we put everything to the test. We take a real, de-identified patient end to end. You move through taking the patient history, forming that PICO question, searching the evidence, appraising it using all those skeptical techie stats we just covered, and finally making a clinical decision. It elegantly ties the complex statistical deep dives of Lesson 8 right back to the human element we introduced in Lesson 1. I'm going to leave you with this provocative thought to chew on as you explore further. No matter how robust the statistics are, no matter how rigorous the trial was, or how narrow your confidence interval is, how do we apply this evidence to a unique patient sitting right in front of us who completely breaks the mold? What happens when the human doesn't fit the trial average? That is the true art of evidence-based medicine, and it's where your critical appraisal skills truly begin. Thanks for joining me on this explainer, and definitely keep questioning the data.